How do you do, ladies and gentlemen, and boys and girls, and mothers and fathers and people? I'm Julius Sumner Miller, and physics is my business. And we come once more to the subject of heat energy transfer. In an earlier program, I talked about heat energy transfer by conduction. And then I talked in another program about heat energy conduction by the mechanism of convection. And let me remind you that for conduction, we have, say, a metal rod. Nothing goes, no stuff moves very far. Energy is what goes. But in the case of thermal energy transfer by convection, we had the actual motion of stuff, like hot air and hot liquids and stuff. So in these two, we had transfer where there was something. Now we come to heat energy transfer by the mechanism of radiation. And this is a puzzling sort of thing because it works best, as I like to say, where there ain't nothing. For example, the heat energy of a star called the sun comes mostly through empty space. So, radiation. Consider the following. Quite a marvelous thing to contemplate. Here I have an incandescent lamp, and I'm going to excite it momentarily, that is, connect it and energize it so it burns, it lights. Now watch what I'm going to do. I'm going to connect it, put my arm here, and I felt it hot right away. But that is still cold. That's a marvelous thing. So the radiation from that lamp reached my arm over this distance of a foot, which isn't very far because this radiation travels at the velocity of light, which is about 186,000 miles per second. So it didn't take very long to get to my arm. Still, the glass did not have enough time to be thermally excited and to warm up, as we say. So my arm was warmed by radiation. Another demonstration. Several programs of mine, and this one also, have opened with this little radiometer. And I am led to say to you that although this is a commonplace little device, would you believe it, it has not yet been thoroughly understood. So I invite you to go to the physics literature and read about it. There have been at least 1,000 notes in the journals written about this, but I will say a word about it. I am covering it from the radiation from the lamps in the studio, and when I remove my hands, we will find that its speed has slowed down very, very much. Then when I expose it to the radiation, its speed will pick up. Now, the vanes in this little rascal are very light and blackened on one side and shiny on the other. And if you look circumspectly at its method of rotation, you will find that the black faces always retreat from you, the observer. Now, I'm going to take my hands away. Look how slow it is. And look how much faster it's going. Very much faster. And the black faces are retreating. Now I have another one here. And this one isn't going, well, I excite it a little mechanically. That one isn't going at all. And I leave that as a puzzle for you. Why isn't this one turning? Why isn't it turning? You see, I consider raising paradoxes and dilemmas and uncommon questions much more virtuous than just talking answers. Next demonstration, which is a most unreasonable thing. Very unreasonable. Indeed, reason is ravaged by this demonstration. We will look first at 3 cans that I have. I have 1 can, 2 cans, 3 cans, and to begin with, they are identical. Here they are. Here they are, 3 cans. From fruit juice, let us say. Now, one of them I left shiny. The other one I painted on the outside black. And the third one I covered with a very thin layer of asbestos. Asbestos. Right. Shiny, black, asbestos. Now, what am I going to do? A wonderful demonstration. I'm going to put some hot water in these to the same level in all 3 cans. Water, 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 and a cover, if you wish, with a hole in the cover. and put a thermometer in each one. A thermometer. We will imagine that I have it right here. Here is a little stick which we understand is a thermometer. Now, this is hot water. 140 degrees Fahrenheit, say, which is about the temperature which you take a bath. Now, question. I let these stay here on the tabletop, and as time goes, they cool off. In what order do they cool? Or more exactly, which one cools the fastest? Now, nearly everybody in the world says that the black one cools the fastest because black bodies are good radiators. Now, part of that is true, but that answer is not correct. I'm going to tell you a strange thing. Because I am a kind-hearted fellow, I'm going to tell you. But having told you the answer, there is a greater mandate upon you to find out why it is so. Here it is. The one that is covered with the asbestos cools the fastest. Now, who'd have thunk it? That verb is the past pluperfect subjunctive of the verb to think. Who would believe that the one that's covered with asbestos would cool the fastest? And yet it does. And I will give you a hint. The program this program, bears on the subject of radiation. And therein lies the secret. So, shiny can, black can, asbestos-covered can, thin layer, very thin layer. Another commentary. Here I have a fourth such tin can, and I have put 7 layers of that asbestos. 7. And this can is brought down to the property of the shiny one, which is an amazing thing, absolutely. No one believes it. Next demonstration. The case of the 4 thermometers. Notice the title I give it. This is not a case for Sherlock Holmes, but for Julius Sumner Miller. Problem. I have here 2 identical thermometers. 2. Absolutely identical. This one, however, is painted white at the bulb, and this one is painted black. Now we will imagine that I go out into the sunshine, into an open field, with these 2 thermometers. To begin with, they read the same temperature. We let a little time elapse. Certainly, they show a rise, an elevation, a growing temperature. Question, what exactly do we see? Now, when I ask this, very few answer it correctly, but I'm going to tell you, again, because I'm kind-hearted. This one, the black one, shows an elevation much quicker, faster, sooner than the white one, but after a while they come to thermal equilibrium with themselves and the surroundings and read the same temperature. So, having told you about a white thermometer and a black thermometer, I'm going to raise another question. Here I have 2 identical thermometers, and they are wrapped at the bulbs with cotton batting. Here you see the cotton batting is very tightly fixed. Here it is very puffy and loose. And what I want to say about these is this, that the same weight of cotton batting is here as is here. So the same amount of stuff insulates both of them. Now I go out into the sunshine with these 2 thermometers, and I ask you, what do they show immediately? And this is a wonderful thing. And I'm just wondering if I'm kind enough in my heart to tell you, because I've told you so much already. I'll leave this for you to explore. But let me say that this is why, for example, it is on occasion useful to wear clothes that are not too tight-fitting. And I have given you a hint about these 2 thermometers. More on radiation. The so-called thermos bottle, a Dewar flask, Dewar, D-E-W-A-R, Dewar, James Dewar, an Englishman. How is this made? Well, I'm going to show you. It is a glass bottle with 2 walls, an outer wall and an inner wall, closely sealed tightly, and the air between is taken out, and if we could see very sharply there, I'll play that to the camera. There is a little tip of glass where the vacuum pump has been connected. It's very difficult to see. Let me see if I can get another one. Oh, yeah, may be able to get this. There it is. There's the tip of glass, sealed off, with the air between mostly taken out. Now, a question I like to ask. You see these little pads of felt. There's one there and one and one. And I ask, where are they? They are not on the outside. They are not on the inside. No, they are between the two walls of glass. So, as one might say, they are on the inside of the outside or the outside of the inside. Now, to more properly finish such a container, we silver it also on the inside as well as on the outside. Why? To minimize the radiation losses. Indeed, as you know, we can put some stuff in which is cold and it stays cold, or we can put some stuff in which is hot, which stays hot. So we have talked about radiation. And now I have a classical problem which you can investigate in a private way with much fun. Problem. Problem. I call it the problem of the black coffee. Here it is breakfast time. Breakfast time. I pour me a cup of black coffee. Here I am pouring a cup, and here is the cup of black coffee. Now I am a user of cream in my coffee, so I am on the verge of adding cream from the pitcher, and let us say it's cold cream from the refrigerator. I'm about to put the cream in the coffee when the phone rings. Ding! Now I have to go answer the telephone, and I expect, of course, to be delayed a little time. Question. I want to find my coffee as hot as possible when I come back. Should I then add the cream before I go to answer the phone, or should I wait until I come back? See, they're a beautiful thing. And I wonder if I should give you a hint. The hint is this. It depends also on this business of radiation. And I want the coffee to radiate away its heat energy at a lesser rate. And therefore, I should add the cream at some time in this discussion. So, you see, ladies and gentlemen, this business of thermal energy, incredible. And when one talks about radiation, he has to have in mind the large-scale view of our entire electromagnetic spectrum, which includes the visible, only a small part of the whole region, the infrared, radio waves, electric waves, ultraviolet, X-rays, gamma rays, and as I am led to say, who knows what is beyond. And I thank you for listening.